Hi, welcome to lecture 13. In this lecture, which is actually going to be in two parts, we're going to be looking at the derivatives of the trig functions again, only more from the point of view of why is it that they are the way they are. And more importantly for you, for most of you anyway, this will include a review of a lot of trig that you need to know. So let's start with the basic question, which is what about the simplest, the first, most important of all the trig functions? How do we calculate the derivative of the sine? Now you already know the answer. The derivative of sine is the cosine, but why is it? Why is it? That's a remarkable fact. Why is it that the derivative of the sine is the cosine? Or why is it that the slope of the tangent line to the curve sine of x can be calculated by plugging in the x value into the cosine? That's a remarkable thing. Well, we have to appeal to the definition. And the definition, we'll use it in the h form, is the limit as h goes to 0 of sine, well, it's f of x plus h minus f of x over h. F is sine in this case, so it's the sine of x plus h minus the sine of x all over h. Now at this point we need a little bit of a trig identity from way back. Let's draw it down here. So here's one. It's called the addition formula. I don't know if you remember this, but if you take the sine of a plus b, the sine of two angles added together, the formula for that is the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first. Right? So we'll use that fact right up here right away. So this is the limit as h goes to 0 of sine of the first cosine of the second plus the sine of the second cosine of the first, and then we still have a minus sine of x. And all that's going to be divided by h. Right? Just check that addition. Sine of a plus b is the sine of a, that's the sine of x, times the cosine of h, plus the sine of h times the cosine of x. Alright, now the question is, what do we do with this? Because it's just the same as what we started with, and we still have a 0 over 0 situation here. So we'd like to factor something, but there isn't anything that factors out of the whole thing. But you'll notice that there's something that factors out of at least two of the terms. So I'm going to try that and see what happens. This is the limit as h goes to 0 of, take that sine of x out of the first term, leaving you with cosine of h, and take it out of the last term, leaving you with minus 1. And I haven't forgotten about the middle term. That's still there. That's the sine of h times the cosine of x. All that is still divided by h. Okay, now I'm going to rewrite this whole mess as two limits added together. And remember that what's happening here is h goes to 0. And as h goes to 0, what happens to sine of x? Well, the answer is nothing. Sine of x doesn't change. X doesn't change as h moves. This changes. But sine of x doesn't do anything. Similarly over here, cosine of x isn't going to do anything. So cosine of x, sine of x are constant relative to h changing, h going to 0. So what that means is that I'll be able to rewrite this expression in kind of an interesting way. I'm going to write, well, we'll do it in one more step. Limit as h goes to 0 of, I'll take that sine of x by itself, and then I'm going to write cosine of h minus 1, and I'll put that over h. Now that is how you multiply fractions, because this sine of x could be sine of x over 1. And then I'll write the limit here, because the limit of a sum is the sum of the limits. Limit as h goes to 0 of, and then I'll have this sine of h over h. Now here's what I'm doing. I've got a common denominator that I'm adding, or really what I'm doing is splitting this fraction into two fractions with the common denominator of h. And then I've still got this cosine of x over here. Okay, so as I said a minute ago, this sine of x is constant relative to h going to 0. So it's going to sit there while we take the limit of this, because the limit of a constant times a function is the constant times the limit of the function. Same thing for this guy. It's going to sit there while we take the limit. Now at this point I'm just going to tell you what's going to happen, because we're not going to go into all the details at this point. But what we will see is that this limit right here, or rather the limit as h goes to 0 of sine h over h, that limit is very, very important. We've played with it a little bit in the lab, but it's going to turn out to be 1. And this limit, which is also a 0 over 0 situation, but this guy has a different limit. This guy is going to end up going to 0. So that when the dust clears, you're going to get this sine of x multiplied by 0 and this cosine of x multiplied by 1, so that you end up with what we know to be the derivative of sine. And that's how it happens. Now I haven't proved these two facts yet, but I am going to do that. This fact is going to take a long, long time. But once we have that fact, this one turns out to be immediate, and we'll do that right now. How do you get the limit as h goes to 0 of cosine of h minus 1 over h? And the answer is you use a trick. You use the trick of multiplying by the conjugate, which, believe it or not, works. Cosine of h plus 1, top and bottom. So that's going to give us the limit as h goes to 0 of, now you multiply that by the conjugate so that you get the first thing squared minus the second thing squared. So we're going to get cosine squared of h minus 1 squared, and that's going to be divided by h times the cosine of h plus 1. At this point I need to whip out another trig identity. We had one here that comes in handy occasionally. We'll box that off by itself. And then there's one that you all should know, very, very important. Sine squared of anything plus the cosine squared of that anything always equals 1. So in particular, right here, I could write this 1 as sine squared h plus cosine squared h. And if I do that, then it's not too hard to see that this limit is going to simplify to the limit as h goes to 0 of, let's see, cosine squared is there, minus this thing, which is sine squared h plus cosine squared h. Any angle, right? So the cosine squareds are going to cancel, and then I'm subtracting also the minus sine squared h. So I'm going to end up with minus sine squared h. And on the bottom, I still have the same thing, h cosine h plus 1 in parentheses. Okay, now here is where we're going to use a simple algebra trick. I'll split this into two fractions. Limit h goes to 0 of, and I'll put the sine squared as sine h times sine h, so we'll peel one of those signs off, and then we'll put this minus sine h over the rest of that stuff, cosine h plus 1. Now this is how you multiply fractions. You multiply the tops and you multiply the bottoms. Well, This limit right here, sine of h over h, is the one that I told you is going to come out to be 1. So this limit goes to 1, or this fraction goes to 1. And what about this guy? Well, it's not that bad. It's not even a 0 over 0 situation, because certainly the numerator, sine of h, goes to 0 as h goes to 0, because the sine of 0 is 0, yes. But notice that cosine of 0 is 1. So this goes to 1, so the entire bottom ends up going to 2. So this term goes to 0 over 2, multiplied by 1, so the answer to that is 0 as promised. Now, of course, that relies on knowing that the sine h over h has a limit of 1. And as I said, we haven't proved that, and that will have to wait until the next video because there's a lot of stuff involved in that proof. A lot of trig that I need to review, and I'd like to do that all separately. All right, what I'd like to do with the rest of the time in this video is look at the derivatives of the other trig functions one more time. I'll put off the derivative of cosine because I want to do that at the beginning of the next video. But let's take a look at the derivative of the tangent. How do we get the derivative of the tangent? Well, I'm not going to go to the definition and try to do all kinds of trig identities because I now know derivative of sine and cosine. I've already proved sine. I promised you that I would do cosine without cheating and using any of these others. So the derivative of the tangent we will use by using the definition of tangent in terms of sine and cosine. So tangent is sine over cosine, and that allows me to use the product rule. So the derivative of a quotient is the bottom denominator times the derivative of the numerator. We know the derivative of the sine is cosine now, minus the numerator times the derivative of the denominator. The derivative of cosine is minus sine, and we'll see the proof of that at the beginning of the next video. And all of that is divided by the denominator squared, which will be cosine squared. Notice that this is minus minus, which makes it a plus, and so you're going to end up with cosine squared of x plus sine squared of x, which all of you should recognize as 1. So this is 1 over cosine squared, and then you need to remember the definition of the secant. The secant is 1 over the cosine. So what we have here is 1 over the cosine, or secant squared, and that's the derivative of tangent. Right? Let's do secant. Well, what's the definition of secant? We were just looking at it. The definition of secant is 1 over cosine. So this is the derivative of 1 over cosine. And once again, there's nothing to this. It's just the product rule. Excuse me, the quotient rule. So it is the denominator times the derivative of the numerator. Well, the derivative of 1 is pretty easy. That's 0. Minus the numerator, that's 1, times the derivative of the denominator. Derivative of cosine is minus the sine. And all of that is divided by the denominator squared. So this reduces to 0 minus minus makes it plus sine of x divided by cosine squared, which is a perfectly good answer, but we normally remember the derivative of secant in a slightly different way. So I'm going to write it as 1 over cosine x times sine x over cosine of x, which is secant of x times the tangent of x. All right? That takes care of the derivative of the secant in terms of the formula that you're supposed to memorize. We can also do the derivative of cosecant and cotangent in exactly the same way. Each of those is a quotient, so you're going to pull out the quotient rule and blah, blah, blah. Okay, that'll be a good place to stop. for the moment, and then we'll come back and do the heavyweight stuff.